Is voice clear? Voice fully clear? I'll start then. If fully clear, comment first. If voice is fully clear, I'll start. Voice and display, both are okay? Okay. Start heading. I think, don't know. See, the rain looks like waiting for my class. Slowly started sound now. Okay, leave it. Put the heading. Red color I don't want. Actually, see. Columns and struts. Heading is columns and struts. That is the technical name used everywhere. But actually, it is columns or a vertical member subjected to axial compression. So you can make a note. Actually, short member, see, in case of roof trusses, see, you get members like this here. Here, some members will be in compression. Some will be in tension, etc. Then, those members are quite short and they are usually called struts. Some name, it hardly matters. Even they are also like a column only, see. Once again like a column. So instead of wasting time on all those things, I will consider main heading is columns. Columns, see. That is for our class, it's a vertical member. You should write all these things. Vertical member subjected to axial compression. Remember, axial compression, say P, P and P. If that is down, this should be up. Together, member will be in compression. Take the length of member as L. Now remember, end condition pending. You write here. End condition time being pending. It will come slowly one after the other one. So take a member of length L, then subjected to, I should write all these things. Consider a vertical member of length L subjected to axial compression P. Later this P will become PB for buckling load. That is later. General P. Then, if I take cross section here, see, for the cross section, you cannot see here, see, for the cross section, A is cross sectional area. And in general, I is moment of inertia of cross section. This I will discuss in detail after the basic derivation. See, in the column chapter, the term moment of inertia, that is not for short column. When you consider buckling, long column, the term moment of inertia is the most powerful. Actually, this I will be later changed over to what? Not that we are changing I. You will write I in some other form, some other term, where area will come. Any idea? This I will be replaced by area and one more term. Tell one more term. Not right now, little later. You know it, I think. Radius of gyration, R. Later A and R. But time being, take I. Now, make a note. When you consider the cross section, it can be rectangular section, circular section, I section, any shape. Through CG, there are infinite axes passing. See, through CG, there are infinite number of axes passes. Now, then area is area, that's all. When you tell I, see, I about XX, I about YY, I about some other axis, I about some other axis, infinite number of axes. Tell me, anybody can tell which I you have to consider in strength of materials. I will tell the reason later. In strength of material, very important, we consider length L constant for, later I will tell you, whether it buckles this way or buckles this way or buckles this way, whatever way it buckles later, we will take length constant. And end condition same for all the axes. But later, it is not that way. In the RCC all, sometime for a column, with respect to one axis, length can be more. With respect to other axis, length can be lesser because of restraints. That all you study in RCC or steel. If you remember, in steel, I told all these things. Effective length on this plane, effective length on that plane. RCC I told 100 times. Steel also I told 100 times. Yes or no? Not once. Repeatedly I told. Yes or no? Different value of, different what? Effective length. That is correct. But what you do is, see, when I take this chapter for strength of materials, those things we can't discuss. Why? Imagine somewhere here one beam comes, here there is nothing, here unsupported length is more, here unsupported length is lesser. Those things all in strength of materials we can't consider. So later I will tell you, in strength of materials we consider length L and end conditions identical with respect to any axis. Not now, but time being someone will ask, sir, why length and I came? It will come later. Okay. Now, first consider, let initially, to understand correctly, let the column be very short, very short. Like, for example, say pedestal, huge pedestal. See, for a column, you can write, for a column of, say, for example, some 300 by 500 column, pedestal is, some extra will be there, some 450 by 650 or 750. Height is just half meter or 1 meter like that. Tell me, will it buckle? Tell me, will it buckle? Will it buckle? No. Or initially you consider column to be very short. Buckling will come in another after 5 minutes. So, okay, now see, short. That is, see, cross section huge compared, see now, see, I will take rectangle section this way. See, you can see here, huge cross section, small length this way. Or I will take a demo member here. Is there anywhere here? 1 minute. Somewhere it will be there. Okay, I am not able to get it. I actually used to have one or more here. Okay. See, something like this, made up of steel or wood. If I compress, will it buckle? Tell me. If I, see this member, if I compress, will it buckle? Common sense. It can never buckle. So, this member, see, if we apply axial force here P, this is also P. Remember, self weight is not considered because if you apply P here, by the time you come here, extra weight of P plus self weight will come. So, even the compression will vary linearly. Say 1000 kilonewton, 1010 kilonewton. 10 also will not be there. 1003 kilonewton. Who will bother about the, see, if you draw the axial compressive force diagram, it may come like this. See, it slight more. 1000, 1003. They will tell take 1000. That all in the practical you consider. Here basic theory, or you can do one thing. Imagine member not this way, apply the load. See, compress this way. Both are same. If you compress this way, self weight will not create compression. It will transfer to the support. So P and P. Now see, thousands of times I told you, I should not tell. Tell what is this one? When you apply axial force, see, these all you should know. When you apply axial force here, what is this is called? What this is called? What that hatched portion is called? That is called cross section. This is called cross section. No, it is called cross section. And for the cross section, let A be area. A be area of cross section. Now, if member is very short, then what will happen? Member will be subjected to, see. Now here cross section will be subjected to axial compression. Axial compression, say P. Therefore, axial compressive stress. Axial compressive stress. Say sigma axial. Sigma A I will call equal to force divided by area. Correct? Force by area, this will be uniform. Uniform for the cross section. In the cross section, where you consider it is same, it is P by A. Now you should write all the statement after the class. Now, imagine right now column is safe. See here, right now no problem. It is taking the load. Now, if you increase the load, what will happen? If you increase the P, as P increases, A will not change. Some will tell, sir, A will change. Yes, correct. Tell why. When you apply axial force P, stress is sigma A or sigma axial, by Young's modulus will give strain, then into Poisson's ratio will give lateral strain. So because of lateral strain, cross section will slightly change. That's all not considered here. So lateral strain due to axial force is ignored. Or if you take a short member, see such a huge area is there, will it be appreciable? The change of cross section area due to lateral strain, will it be appreciable or neglected? Time being, is it appreciable or neglected? See, first of all, that is a problem. Some people are there, they will tell, sir, cross section will change area. Yes, correct. I will tell, I know that one. No one thing I am not knowing. Tell me, is it appreciable or negligible? It is neglected. We don't consider it. So, since A is constant, as P increases, axial stress will also increase. Now, for every material, there is a limit or ultimate strength in compression. The ultimate strength in compression. Compression, remember, for short member, pure compression, or you can call it as crushing stress. Crushing stress. Okay. Now see, as per IS code, stresses are not sigma. Stresses are called F. So you can call this as, in IS, when you change your to RCC steel, you have to call it FA. Here sigma A. Crushing stress, sigma CR. Or in RCC or steel, FCR. See, for steel, it is called Fy. And for RCC, we take it FCK. Heard of it? RCC crushing stress, we take FCK. Steel, we consider Fy. Yes or no? Actually, in steel, Fy is the yield stress. It is not crushing stress. Crushing stress is more than yield stress. But for safety reason, IS code told no, you limit to Fy only. Remember, even though it can take more stress than Fy in axial compression, IS code told nothing doing. You take Fy is the limit. Clear or not? Actually, in compression, steel has got more strength than in tension yield. Stress in C, for mild steel, yield stress is taken 250. But compressive stress at crushing value is actually around 325, 330 is there. So, but IS code told, don't consider it. Safe or unsafe? Even though it can take around more than 300, you limit it to 250. Safe or unsafe? Tell me. That is all on safer side or unsafer side. When IS code tells limit the strength. Limit means what? Even if you got more money, you imagine you have lesser money. Safe. So, but strength of materials, I will call sigma CR. Because why? This class I am taking YouTube, it is for strength of materials. 99% people who study, they use sigma. Okay, I will also use sigma. Sigma CR. Now, as the P increases, finally, your axial stress sigma A will approach sigma CR. Correct? For example, imagine crushing strength is 300 Newton per mm square. Just imagine. Now, for a load of, say, for example, 600 kilonewton, stress sigma axial equal to randomly, say some 500 area, some randomly, if you apply 600, imagine stress is 120 Newton per mm square. Tell me, safe or unsafe? If you apply a load of, say, put here, if a load of P equal to 600 kilonewton is applied, let the stress developed by P by A equal to 120, less than crushing strength of 300. 300 random. So, safe or unsafe? Tell me. Will it fail or safe? It is safe. Now, increase the load. Increase P to 1200. Then 120 will become 240. Still less than 300. Safe. That way, finally increase P to, where is my calculator? Ayo, 1 minute. Anybody can tell? Interpolation only. 600, if 600 120 means 300 by 120 into 600. What is the answer? 300 by 120 into 600. What is the answer? My calculator is actually inside because I was going to college from past 4 days. I kept it in the bag only. 300 by 120 into 600. What is the answer? 1500. Okay. So, suppose the load is 1499 point something. Stress will reach what? 299.99 etc. Still less than 300. Okay. Finally, when the load reaches 1500 kilonewton, say, then the stress developed will be, that is by P by A, reaches 300 Newton per mm square equal to crushing strength of 300. Now, member will get what? Tell me. The member will get. If the load reaches to 1500, the member will get what? The stress reached crushing stress. Member will get. It's so simple. The member will get what now? One simple word. The member will get. Why nobody is commenting? The member will get. English. Not failed. Use the correct word. Why this much difficulty? Use the correct word. Member will get. You are not answering for such a simple question. See, delay for answering means problem. Okay, I will tell what to do. Usual problem. Member will get crushed. Danger. See, red color. Crushed. Therefore, you can tell 1500 kilonewton is called, this P I can call PCR. What is PCR means? It is called crushing load. It is called crushing load or the load axial force in compression when the material will get crushed. Now, this is the case of a short member. Remember? So later, remember, I won't tell once again. Later, warning. When we consider Rankine's formula, I won't tell once again. Rankine's formula, there we need expression for crushing load. Expression for crushing load. Crushing load. If the column is short, see, if the column fails by crushing, then answer is what? The crushing load PCR, crushing load PCR equal to sigma CR, that is crushing stress into cross-sectional area. You can call in strength of material sigma CR, or in RCC or steel you replace by FCR. If you are going for IS code expressions, instead of sigma CR, call FCR. In concrete, it is called FCK. Steel we take it as FY for safety region. Clear now? Clear or not? You are not answering. If you don't answer, I can't proceed. Clear? By stress equal to force by area, force equal to stress into area. I will not explain once again. And remember, this FCR is constant for a material. It is constant for a material, or it is the material property. at what stress it will crush. Okay. But crushing load depends upon cross section also. Okay. This is for a member which fails only by crushing. So tell the condition, member should be sufficiently short or cross section should be sufficiently huge. I will tell later. See, suppose a member has small, high length. When a member has got lesser length, you cannot tell member having lesser length is short. No, not only length, cross section also considers. This all I will tell when I go to buckling. Then I will tell, not right now. So this expression we got. Now leave this one now. Now come to buckling of the column. See, now come next please consider buckling. Consider buckling. Buckling. Some people call buckling as crippling. Sorry, I don't call because in IS code steel, buckling is separate, crippling is separate. Crippling is a local failure at the junction of web and flange. It will get crushed there. Buckling is overall web buckling. See, in IS code later, in I section solve, web will buckle. And see, the web that is buckling. Whereas, see, this is the I section. This is buckling. This is what? Crippling. Therefore, I will use the word buckling only. But sometimes people call it crippling. Okay, no problem. But same person in steel he will tell, no, the buckling is separate, crippling separate. Then why should I call crippling now? I will call buckling. Okay, see. Buckling is actually another form of bending. Bending. Okay, now, 1 minute. I will show what is the buckling. See, I will show a simple example. Take a scale. See, this member is very thin and actually very thin. When member is very thin, it is called slender. See, now, if I take this member there, apply axial compression. See, you can see, I am applying light load. This is already bent. Why? Because of huge bending. Don't see that one. See, if I apply axial compression lightly, nothing happens. See here, it is okay. It is taking load. As I increase the load, see now correctly. Oh, can you see buckling? Can you see or not? See. You should write here. He took a scale from both hands. First he applied a small load, very light load. We can see member straight. Later he increased the load. Suddenly you can see, it will buckle this way. It can't buckle that way. That I will tell once I go for buckling load discussion. Not right now. When I discuss about moment of inertia, then I will tell you which is the axis for buckling. Right now you see buckling. See now. I will increase the load. See, now buckling. Or if I take the book, see here, book, light compression, standing, see now, gone. Whereas if I take this pen, see now, no, it is not buckling. Huge load required. Clear buckling? How buckling will take place? Clear or not? Okay, now come to buckling of column. What I will do today's class is first I will explain all the basic concept involved for buckling and go for expressions. And later class I will discuss lot of concept about buckling, etc. Maybe too much of concept is there, huge discussion is there. Therefore, I may not take that class here. On that day, I may shift it to Zoom only. Why? General public, nobody want to discuss that way. They will tell you storytelling. He is telling complete discussion. Therefore, better. Then after that discussion class, when I come back here, I will continue further. Okay. Now, see, consider buckling. That is nothing but bending only. Now, first, you have got expression called Euler's buckling load. Buckling load for very important long columns. Long columns. See, the person Euler, he derived expression for buckling load for a long column. And very important, long column means what a long column? It is long means depend the long term. Make a note. You should make a note. Long means not only length, also what counts. See, a 2-meter column can be a long column, whereas a 10-meter column can be a short column. Remember, a 2-meter column will become long column. What is this, you will tell. Whereas a 10-meter column, you tell, oh, a short column. See, suppose there is a huge cross section, say 600 by 600 RCC. Even if it is 10 meter, 10,000 by 600, it comes to how much? 6,000? Not 10 meter. Say for example, 6 meter or 6 meter. The ratio comes to only 10. Up to 12 in RCC, we take short. Whereas a column of, see, just slender, 200 by 600, even if the length is 4 meter, it's a long column. 4,000 by 20 is 20. See, here, which one? Length by lateral side, lead side is actually how much? 10. Here, length is smaller, but because of the weakness of the side, the ratio, so you make a note, when you define long, it is not only length, what consider, and not only length, but also what considered not only length. See, suppose one person, see, is fined 10 crore rupees. Another person is fined 1 lakh rupees. You cannot tell who is severely fined. It is possible that the one who fined by government for some reason, penalty 10 crore, he may laughingly give it. He will tell, okay, no problem, I will pay immediately. The person who got a penalty of 1 lakh, he may escape and what? He may leave his place and become what? He may become gayab in Hindi. Gayab. He cannot manage. Even 1,000 rupees he may not manage. So depends upon his capacity. So you tell long not only on length, but also what considered? Tell me. What considered? Not only length. No. Slenderness ratio later, not too early now. Slenderness ratio you should define, then I will consider. Simple language. Not only length, but also what considered. Okay, slenderness ratio correct. That is, you are going ahead actually. I can't go ahead. You should go in order. So, not only length I told you, but also what? One more, see. No, end condition later. It will come one by one. End condition will come one by one. Suppose you maintain same end condition, same material. So, also what? See, I am telling you. Also, simple language. Simple end conditions, all that is advanced. We will go to it, no problem. I will consider each and everything. But also, main, one is length, other is cross section. So, other is cross section, right? Also cross section. See, and then also material also counts, and end conditions also counts. That are secondary, not right now. So, or remember to be long, it should be sufficiently long, or it should be what? It should be thin. If member is long or very thin, then there is chance of buckling. Okay. Now, Euler's buckling load is for column, long column. So, but I won't write. See, a long column is 1. A long column is 1. You should write definition. A long column is 1 which fails only by what? You should write it. Those who are interested should write. Which fails only by what? A long column is 1. See, which fails only by, see, what? No axial stress, nothing considered here. Which fails only by buckling. Only by buckling. Okay, sufficient, leave it now. Now, that's all. For all further discussion regarding some assumptions, initially straight, axial load all, I can tell only after the derivations are over. Because why? Once you know the derivation part and you get the idea how buckling load comes, Then doubt comes. If that parameter is that way, what will happen here? Easy to discuss. If I keep on telling now, waste of time. So time, leave it now. See. Now, heading is Euler's buckling load for a long column. For a long column. Remember, Euler's formula is applicable only for long column. Okay. I just now told a long, so for applying Euler's formula, condition, it should fail only by buckling. This all you are right. Or a long column is one which will fail only by buckling. Okay, now what we will do is, see, consider a column of length L. Length is L. My simple language, length L. Later, one more term will come called effective length. In RCC, it's called L effective. In steel, it is called KL. Both are same. Here, L. Effective length will come after I finish derivation. Right now, L. Then, let A be cross-sectional area. Now, one most important term. See, for strength of materials point of view, in strength of material, we do not discuss those things all. Which one? In one plane more length, one plane less length. We don't consider. Or simple language I will tell. Later, L effective will come. At that time, in strength of material, L effective is constant with respect to any axis in the cross section. Whether you take XX axis or YY axis, effective length is same in strength of materials. But it is not same in RCC or steel or precious concrete or practical. That you learn at that time. Therefore, now one most important. I will not tell repeated because sometimes people will tell, sir, you told I is the least moment of inertia. But that column, because of the different length in the different planes, higher I also counted. I told C correct, I will tell what I told earlier. Strength of materials, we don't discuss those things all. RCC, do you think I am not knowing? See the RCC class. Okay. Now most important, see, when the column buckles, see, this way, cut it, or do one thing. It can buckle this way all. See, column, cut. See, imagine a column here. It buckles, cut. End condition, I am not bothered. Cut here, buckles. Then, this buckling is actually nothing but bending. Yes or no? Tell. The buckling is actually nothing but bending. Just tell me yes or no. See, all these things you should write. If you want to understand, everything you have to write is bending. Yes. Now, and from the initial line, what it has undergone here, that is called what? In case of beams, if a beam bends this way, tell what you call this one and this one. What you call this one and this one in beam question. In beam, this is called theta, this is called y. Theta is called slope. Angle made by the tangent with the beam axis. This y is called what? What that y is called? That curvature later. What is y is called deflection. Y is called deflection. Therefore, see, suppose a column, see, some column is there. See here. It will buckle. How it buckles? I will cut it here. Cut. It comes this way. It continues. Why I am not continuing? Because, see, it may come this way, or who knows, it may come what? This way, all based on what? Boundary conditions. Intermediate, okay, intermediate, cut. This is the original line, This is the deformed shape. You later, I will use blue color for this one. See, now, tell what this is called. In beams, what do you call it? How much any point got linearly displaced. What do you call? Deflection. Adya English? Okay. No, displacement bada. See, don't call displacement because Theta is also displacement. One is linear displacement, other is angular displacement. We call it simple language. See, displacement means theta and y both are displacements. Simple language, linear displacement, simple language. You are going to complication. We call this as deflection. Tell yes or no. We call this as deflection. Oh, okay, vertical, in the beam, it is called vertical deflection. In column, deflection is horizontal. And if I draw tangent anywhere, okay, 1 minute here. I will call somewhere here, okay. I will call somewhere here. Okay. This is called deflection. Deflection, that is y, horizontal. See, some will tell horizontal is x. No. Here also, along the member we will take x, and deflection you take y. And if I draw a tangent here, tell what this is called. If I take tangent, what this is called? This is called slope or rotation or theta. Tell yes or no. This is called slope or rotation or theta. Tell yes or no. Fast. You should not waste time now. Yes. And you should know that this theta, tan theta equal to theta in radian equal to, do you remember? dy by dx. Yes or no? Very important. The tan theta, that is theta, equal to dy by dx. Correct? Correct or not? Tan theta equal to in radian y by dx, dy by dx. Y by dx. Y by dx. It is dy by dx. Okay. Now, what I will do is, I will go for first. See, we have, when you, in strength of materials, we have to go for, see, end conditions. 4 standard end conditions are considered. In 4 standard end conditions are considered in strength of material. Right here, some will tell, he wrote 4 standard end. You write it, those who are other public. 4 standard end conditions are considered in strength of materials. Practically, there are so many end conditions. See, there is no pure fixity. There is rigid joint which will undergo displacement. Sway effect is there. For that all, IS code has given what? How to consider effective length. Basic subject point of view, 4. See, one of them. First case is both ends are pinned. See, first is both ends pinned, hinged or pinned. Hinged or pinned, both are same. Pinned. That is the first standard condition. Now, second condition you are considering is, second one, both are fixed. Practically, both fixed will not come by. It is not possible to achieve fixity. So, for that correction is there. Okay, now, next will be 3. I am writing briefly because why? I am covering one by one. Next is one end fixed and other hinged or pinned. See, any side, either this way or this way, but usually nobody likes this way because usually for buildings all fixed is at the base. So here, over. Last one end fixed and other free. See, this way. For everything, you apply the load. Axial compression P. No P. Now, let P be buckling load. Let P be buckling load. I am writing roughly because why? Everything I am writing neatly now. See, P be buckling load. Now, immediately definition. Buckling load is the load at which column will what? Buckling load is the load at which column will. Buckling load definition. Buckling load is the axial compressive load at which column will. No, that is wrong statement. I'll tell you why. For example, I will take the scale. Okay, agreed? See now. I will do one thing. I will apply a load of 100 kgs. See, buckles. So is the buckling load 100 kgs? Or I will take this book I will apply 100 kgs. How I apply? Heavy load by a machine. Is 100 kg buckling load? Is 100 kg buckling load? No. Buckling load is the load, or buckling load is the least load at which column will start buckling. See, for example, apply 10 kN load, no effect. Apply 10.6 kN, suddenly buckling comes. Now you apply any load more than 10.6, it will buckle. When 10.6 it started buckling, you apply 100 kN also, it will buckle. But tell what is the buckling load then? Buckling load is what then? 10.6 kN. It is the least load at which column will buckle. Fully clear? Definition. Buckling load is the least load at which the word least, very important. No, clear or not? The word least is very, very important, because we are, is it clear or not? The word least is very, very important. I will tell you why important. Clear? The word least, it is very important. Yes, because later we are going for trigonometric functions. At that time, you should take the least value for the what? The trigonometric function. See, that's why that least, I will write there, considering the least value. Some will ask, sir, why least value? I will tell them, start from class from beginning. Don't come now and comment. There are people who suddenly come and comment, sir, why least? Why least means I want least, keep quiet. Because he came just now, and now he want to know why least. Go, leave the class or continue. After the class is over, go back to full class. Then you will tell, oh, I won't ask the question. So the least is very, very important. Later, when you go to trigonometric function solution, you should take the least value. Clear or not? I will not tell one word about it. I will just write considering the least value. Okay, done. I will only tell consider the least value. Over. Now, first important is now consider buckling load. See, before you start considering Euler's buckling load, 4 cases are there. I first thought I will derive only one case, remaining I will give formula. No, this chapter, even if it goes for little more number of classes, no problem, better understand. Because so many people, examination point of view, they want derivation. So I will make it equally useful for academic purpose. So that, now see, now we are going for derivation of expression for, you see right here, now you are going for derivation of expression for Euler's buckling load, that is PB, for a column with length L, then cross-sectional area A and modulus of elasticity E, and I is the moment of inertia of cross-section. Anybody can tell what I you have to consider? Anybody can tell what I you have to consider? I will tell the reason. 1 minute. What I you have to consider? See, different axes will have different moment of inertia. Which I you have to consider? I will tell one by one point. Which I you have to consider? Which I? Least I. I means, remember, least moment of inertia. I will not least moment of inertia of cross section. Or we will call I minimum or I least. Reason very simple. See, I will tell you. Very simple reason. See, when the member bends, it will deflect this way. See, this is called deflection Y. You know that in strength of material, deflection Y, the deflection Y will always come some property of load and span in numerator. Yes or no? Some terms, see, WL cube, WL power 4, ML square, etc. Numerator will be loading and span. Correct? Yes or no? Numerator will be load and span. See, this is based on load and span, numerator terms. Whereas denominator, you get EI. Yes or no? Denominator, you get EI. Okay, now, what is the meaning of EI? EI is called flexural rigidity. Oh, I asked you and I am telling the answer. Of cross section. Of cross section. So many people, they will tell flexural rigidity for the beam. I will tell them, it is not for the beam. Your length is not counted. You tell technically cross section. When you tell something, tell correctly. It is flexural rigidity of cross section. Now, tell me. Now, how it will deflect? See here. If I take the scale, I apply load. See now, it deflected this way. Why it has not deflected this way? Tell me. Because to deflect this way, it has to overcome. See, or 1 minute. As EI increases, deflection is more or lesser. As EI increases, deflection becomes what? See, as EI increases, deflection becomes less. Good or bad? Good or bad? Deflection is lesser. Deflection less means buckling chance is lesser. See, buckling chance lesser. Lesser. Good or bad? Good. But as EI decreases, tell me, the column or beam becomes stronger or weaker. As EI decreases, it becomes stronger or weaker. Stronger or weaker. If EI decreases, weaker, because deflection will increase. Buckling chance is more. Or when a beam deflects or when a column buckles, it has to overcome flexural rigidity of the cross section. See, now, if it has to bend this way, buckle this way, it has to overcome the EI with respect to this axis. I will tell you later, axis also. Now you believe me. To buckle this way, it has to overcome resistance with respect to this axis. Very huge, because thickness into depth cube, this cube. Very huge moment of inertia. But to buckle this way, it has to overcome only the thickness. Or simple language, you can tell, column will always buckle. Column will. I told you, this is when effective length is same with respect to all the axes. Strength of materials. So, strength of materials point of view, if the effective length is same with respect to, what is effective length will come later, is constant with respect to all the axes, column will always buckle about the axis in cross section about which flexural rigidity EI is least. So common sense, see, where weakness is there, it will buckle. Now, E is constant. Therefore, simple language, where I is what? Tell me. Simple language. I is. Where I is. Simple language. Highest or least. In strength of materials, when effective length is constant. Why I am telling? I do not want someone to tell, sir, defective length means, I told you, see my class full, least. It is least. Therefore, in strength of materials class, we will write one thing. In the entire column chapter, whether you consider Euler's buckling load or Rankine's failure load or some other formula, you do whatever you want. Wherever I comes, you have to consider least moment of inertia of cross section. Clear? You have to consider least moment of inertia of the cross section. Clear? Least I to be considered. Clear or not? Always least I. These all make a note. Why I told least? You tell clear, I will go to end conditions now. Clear? Okay, now 1 minute. Now I will go to Euler's buckling load for 4 standard cases. See, now derivation of Euler's buckling load for 4 standard cases. Namely, case 1, I will start here. Case 1, both ends hinged or some people call pinned. Pinned means not Kannada gund pinned. Okay, now case 2, both ends fixed. Both ends fixed. I will tell you, I am preparing everything. Case 3, one end fixed and whereas other is hinged or pinned. Whatever you want to call, pinned. Okay, spelling problem. Pinned. Last case 4, one end, I am writing roughly because why? Everything, when I write anything, I write neatly. This is introduction. Case 4, one end fixed and other free. Now, make a note. For all these cases, standard, I will write afterwards. Okay. For all these cases, what I want is, first I want to discuss the boundary conditions. See now. See correctly. This is black color is initial position. Black color. Or I will do one thing. See, solid, black color. Both ends are fixed. I will do one thing now. In all the classes, I will take this is A, this is B. This is A, this is B. You can take whatever you want. Here. Why I am telling now? See, this is hinge. A and B. Anywhere you can take fixed and hinge. Last one, this way. A and B. Okay. Everywhere, all the cases, L is the length. Full everywhere, L is the length. Now, I want deformed shape. Sorry. I will project here and tell deformed shape. I will make everything clear today. Maybe I may not be able to derive today. No problem. Understand correctly. Project it. Sorry. I will apply buckling load here, PB. Everywhere, I will apply buckling load PB. If that is PB, see this also is PB. Be careful. If that is PB, this also is PB. Here, if this is PB, this also is PB. Notice. This is before buckling. Remember, this is before buckling. PB, PB. Oh, sorry. Before buckling. I don't think. I will write only P. Okay, better. I will apply a load which is directly possible without what? Without buckling, or a low small load where only axial compression, that is no buckling. Okay, now at buckling state, this P will become what? Tell me. When I consider buckling, this P I am changing over to what? Symbol. When I take buckling, this P I will change over to symbol. Later P will vanish. See, later you tell, hey P, you get out. Your name will be changed later. First time, see, light load, very small load. So that no buckling, nothing. Later you tell, hey P, you are going to change your name to what? To PB. Okay, now PB is the P becomes PB. See, blue color. Now, tell me elastic curve. So I will do one thing now. I will put dotted line end condition here. Light line end conditions. See now. This is PB. Notice blue color. Buckling load PB. Buckling load PB. Column will buckle like this. See. If I draw tangent here, there is slope. If I draw tangent here, there is slope. Fully clear? So here, this is the point A. Notice here. Theta at A is there. Theta at B is there. Tell yes or no? Theta at A is there. Theta at B is there. Correct? Yes or no? Theta is the slope. Pinned end can rotate. Clear or not? theta A is there, theta B is there. Yes, and remember, y is the deflection. Anywhere randomly you take, see now what I will do is, red color, I will take a section. I will maintain same for derivation later also. I will maintain same format so that you can also use the same format and thoroughly understand. See, later what I am doing is, right time, not getting red color. 1 minute now. Same thing. When I want, I won't get it. I here, luckily. Later, idalla, not this one. 1 minute. See, require red color, not getting it. 1 nimisha. Got it. Later, I will take a section XX. Everywhere, section XX. I can take X from anywhere I want. In all the 4 cases, I will take X from here. I will take X from top. Now, this is called deflection Y at X. Clear? See, write a statement. Consider section XX. XX. At X from top. X, you can take anywhere you want. You take from top or bottom, answer will come. One symbol, X from top, in my class top. That is A, everywhere. Let Y suffix X be what? Horizontal displacement at XX, or you can tell easily horizontal deflection. Horizontal deflection. Deflection at XX, YX. Clear now? Fast. This statement I'll tell you later. Take what? Take one screenshot for tomorrow's class. Clear? Okay. Now, tell me. Observe and tell me. Is any other reaction, see, hinge support can take horizontal reaction. Yes or no? See, hinge support can resist vertical, can offer vertical reaction and also horizontal reaction. Now, tell me, any horizontal reaction possible here? See, suppose you by mistake, you write a horizontal reaction here and a horizontal reaction here for equal. See, when there is no horizontal load, if I take HA right side and HB right side, then it will spoil the equilibrium. Yes or no? See, it will spoil the equilibrium. Tell yes or no? It will spoil the equilibrium. Make a note. Yes or no? Yes. Therefore, it can take horizontal reaction, but horizontal, I write blue color. See, it has got capacity for, I'll see later how it comes, yes, correct. It can take horizontal reaction, you write here. It can take HA is possible, HB is possible. Possible, but it will not be there because this is a symmetrical case. See, this is a symmetrical case. You see here, symmetrical case, if horizontal reaction comes, it will spoil the stability or it will spoil the symmetry. So therefore, horizontal reaction, even if it has got capacity, will not be there. Or, see simple language, I will explain, write it now. See what I am doing. I will take this scale, I will apply only vertical load. See now, tell me, buckling, both are pinned, buckling. See, any horizontal reaction, tell me. Both are pinned. Any horizontal reaction? Any horizontal reaction? Because, why I am telling? Because later, when horizontal comes, some will ask, sir, last time you took, see, there is going to be horizontal reaction here. Then some people are there, sometimes troublemakers. They can't create trouble to me. They may tell, sir, you took horizontal reaction here, hinge. Yes, sir, here also hinge. Why you are not taken? Go to my earlier class. Even if you consider, it will become 0. Clear now? Even if you consider 0, or see here, sigma m about this point equal to 0. My HA into L equal to 0. See now, take moment about this point. HA, PB into 0, axial. So HA into L equal to 0. So horizontal reaction capacity is there but not there. ನೋಡಿ, not there. ಇಲ್ಲ, not there. ಸಾಕು, ಕಟ್ ಮಾಡಿದಲ್ಲ ಸಾಕು, not there. Now tell here, both end fixed, how it will bend? The elastic curve, see, this is, I'll do one thing now, this is original. See, now load become PB. I'll put dotted, I'll put the sketch once again. This is the initial position. See, fixed. This is original when there is no buckling. Fixed. Dotted line is initial profile. See, when you derive, if you understand correctly, very easily. Now, elastic curve will become how? It will become like this. See here. It will become like this way. Or, if I take a section XX here, see, if I take a section, it is red color. If I take a section XX here, at X from here, X here, this is called Y at X. Then, you apply a load, the buckling load is blue color. Buckling, tomorrow's class, you take a screenshot of this one and remember, I will tell you, tomorrow next class, when I start derivation, I will tell you, consider the screenshot of today's class. Otherwise, if you get doubt, you have to blame yourself only. I can't do anything. If you get doubt, you have to blame yourself. Now, when buckling comes, this is PB. See, PB here, PB here. Now, if it is only PB, if there is nothing, that's all, what will happen? See, if it is only PB, it is both are pinned. Now see, both fixed end means, see, when the fixed end is there, here, see, fixed end, it cannot allow theta. Tell, when the moment bending starts, tell me here, what reaction will come here? Fixed end, slope should be prevented. See now, if the beam bends this way, see, if the buckling is this way, to prevent slope, tell me, at the top, do you require a clockwise reaction or to get this elastic curve? To get this elastic curve, see here, to get this elastic curve, do you require clockwise there or anti-clockwise there? No horizontal reaction, still no horizontal reaction. Still no horizontal reaction. You tell me, there will be a reacting moment here. Common sense will tell you. See, how is the reacting moment? Common sense will tell you. See here now. Buckling this way. This is pinned end, fixed end. See, it will give reacting moment like this. How? Tell me. Clockwise moment. This moment I will call MA. Therefore, see, I will call this as MA. Now, here, tell the reacting moment. Here, reacting moment. Here, reacting moment. Clockwise or anti-clockwise? At the base, reacting moment. Clockwise or anti-clockwise? At the base, reacting moment. Clockwise or anti-clockwise? Opposite, anti-clockwise. See, anti-clockwise, MB. Now, symmetrical case. PB balances PB, MA balances MB. Now if you take moment about this point, plus MA minus MB, MA equal to MB will cancel. Even now, tell me, horizontal reaction chance is there. See, very important. If this reaction is this way, when there is no horizontal load, it should be like this. See, this is MB. MB. Horizontal reaction chance is there, still it is not there. See, HB, chance is there, still it is not there, because moment will balance moment, load will balance load, symmetrical case. Clear? Even now, horizontal reaction will not be there. Clear or not? Fast. Clear? Even now, horizontal reaction will not be there. Clear? Fast. I have to close this one. Fast. Time is not there. Fast. Don't waste time. You tell clear, I'll go to the next one. Clear. Okay, now, come to the law here, this case. This is P, later, after buckling, see, this is pinned, this is fixed. See, tomorrow when I start next class, this I am not writing. I am writing this sketch actually. Okay, see now. Elastic curve. How it will come? Here pinned. Nodi. Here, one more thing, forgotten. Tell me here. Here, theta, what is this point? Theta A equal to 0. Here also, theta B equal to 0. Tell yes or no. See, here, theta A 0, theta B 0. Correct or not? First. Clear. And I forgot. See here. This is deflection. Theta A is there. But, comma, deflection at A equal to 0 here. Here also, theta B is there. Slope at B is there. But deflection at B equal to 0. Correct? The YA 0, YB 0. Here, theta A 0, YA 0. Theta B 0, YB 0. Or hinged end, deflection is 0, slope is there. Fixed end, slope is 0, deflection is 0. Tell me, fast, clear? Oh, yes, okay, now come here. Here, elastic curve will come this way. See, here what will happen? See, elastic curve, dotted line, dotted line here. See, here, theta is there. Theta is there. See now, here theta is there, but when you come here, it's like a question mark. See here, it will come this way. It will more smoothly on me. Okay, here. Therefore, if you draw a tangent here, this is the point B. This is a point A. This is a point A. This is a point B. This is a point A. This is a point B. At the point A, see, you can tell theta A is there, but deflection at A equal to 0. See, as usual, if I take a section XX at X from here, this is Y at the point X, and here theta B equal to 0, and also deflection, see, rounded are boundary conditions. See, theta YA 0 is a boundary condition. YB 0 boundary. Theta A 0 also boundary. Theta B also boundary. Theta A is there means it is not boundary. It is a no, unknown value. Boundary condition means known displacement. If the displacement is known, then it is called boundary condition. See here. Theta is there. Okay, there. YA 0. Okay, done. YB 0. Theta A 0, YA 0, theta B 0, YB 0. Here, YA is there, theta is there. See, theta A is there, Y 0 is a boundary. Here, theta Y, both are 0. Now tell me. See, A point, I shift here now. A little this side. Little I shift this side A. Because now I have come to buckling load. This is A. Very important now. I should shift slightly here. So, and theta A is there, YA equal to 0 is boundary. Okay. Now tell me, if this is the buckling load PB, this is buckling load PB. Come this side, no space here. Theta B 0, YB 0, boundary. Okay. This is the buckling load PB. Now tell me, at the fixed end bottom, there will be slope 0. There will be a reacting moment. Tell yes or no. At the base, the moment curvature comes here, there will be reacting moment MB here. This is the most important. I will not explain. I will not explain again and again later. There's a here buckling load PB. PB balances PB, but MB will come. No M there. Clear? If this is clear, over. Clear? Okay. Now be careful. Now tell me. This can take horizontal reaction. Horizontal reaction is there or not there? Tell the answer. Think a little and tell me. Horizontal reaction is there or not there? Here, this is unsymmetrical. The moment it bends this way, horizontal reaction is there or not there? Horizontal reaction is there at A. That is HA. Remember, HA is there. Is there. Is there. Therefore, consider. Or common sense, I will tell you. See, PB balances PB. This MB will try to move A which side? See, this moment will try to move. See, this moment will try to move A which side? Tell me, left or right side? It will try to push A to which side? The moment at B will try to push left side. To balance it, right side will come. When that reaction is right side, tell for equilibrium, what is the reaction at the left side? Tell me. Here also horizontal, see this is MB, MB. Here also horizontal reaction is there, HA. Or here, very important, your HA will be equal to HB. And also you can tell HA equal to HB equal to, anybody can tell what is the answer? You can tell the answer. This is most important. See now. PB balances. Leave it now. There's a couple MB. This HA and HB will give what? Opposite couple. See, this HA and HB, HA and HB, HB will produce a clockwise couple. That clockwise couple will balance this anti-clockwise couple. So this will be equal to MB divided by L. Correct? That HB equal to MB by L. Yes or no? At HA equal to HB equal to MB by L. Okay. Or do one thing. Take moment about this point. See. Plus HA into L plus HA into L minus MB equal to 0. HA equal to MB by L. Sigma H0, HA right side equal to HB left side, or HA minus HB equal to 0. Both are equal. So remember, very important. You make a note. See, last I will dictate here now. General, I will dictate here. What I am dictating, right? As per our class deformation considered, for the case of bottom fixed and top pinned, fixed and reacting moment is there. You should not forget to consider horizontal reaction at both the supports, because it will be right side here. By chance you take left side, nothing will happen. Solution will take care of it. But anyway, see, this MB will push A left side, or for the case of one fix, one hinge, this is a special case. Special case of one fix, one hinge. Then at the top, horizontal reaction A is very important. If you forget this one, your problem is gone. You will never get the answer. Clear now? Do not forget. Do not forget. When later I come to derivation of case number 3, I will simply tell what? PB, reacting moment MB, to balance that one, HB, HA. HB right side, HA right side. For those who are not clear, either go back to previous class, study and come back, or don't come to my class. That's all. I should be harsh. I will tell, don't come to my class. My class is not for you, because your standard is too high. I am not having that standard. Then YA0. Clear? This is the most important. This HAC, important. Clear? Okay. Last one. One fix, one free. See now. If I take one more case now, see, now very important, your buckling load is actually here. But here, elastic curve will go, how? This is free end. So, it will go this way. Oh, therefore, see here, there will be vertical reaction PB here and reacting moment MB here. MB. Horizontal reaction is not there. But your buckling load PB was initially here. Finally, it is here. Your buckling load will move. This is the displacement Y at A. There is YA, of course, theta A is there. Here, theta B equal to 0, Y at B equal to 0, boundary here. Here, theta B is theta A is there. But remember, deflection Y at A is YA. Very, very important. In all the previous cases, Y0, 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 no deflection. When one fixed and one free, at the top, see, at the point A, see, this is A. This A will move here. I will put A here now, or A dash. Okay. This B will remain there only. Therefore, here, in case I take a section XX, if this is YX, remember, as you go that in all the cases, see, YX increases, 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 once again 0. But this is a case when YX keeps on increasing, it is a cantilever. YA is actually Y max. Tell yes or no, that YA is nothing but Y maximum at the free end. If this is clear, I will lastly tell boundary condition and close the class. Clear? You tell clear, I will tell boundary condition and close the class. Now, see correctly. Tomorrow there is next class. There is no time to explain all these. So I will tell those who are attending today's class, if you get doubt, you get to clarify from the previous class. So now I want boundary, make a note. I want boundary conditions. Remember, boundary conditions means what? It is what? Tell me. It is always non-displacement. 0 also is okay. If displacement is unknown, it is not called boundary condition. Boundary condition is always non-displacement. कन्नड़ದಲ್ಲಿ ಗೊತ್ತಿರೋ ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ಗಳು ಹಿಂದಿಲಿ जिसको बारे में आपको पता है वही डिस्प्लेसमेंट, जिसको पता नहीं, कितना नहीं पता, छोड़ दो उसको. Clear? Okay, now tell fast. I want write one by one in red color. See here. Everywhere my X is from top. Okay, start here. I write here. See, at the point A, boundary condition. Theta A is there. No, if it is there, leave it. Some will tell, sir, theta A. Okay, how much? I don't know. If you don't know, keep quiet. It is not boundary condition. At A, sorry, YA 0. Therefore, Y becomes 0 for X equal to, fast. Tomorrow, next class, I am not explaining. I will keep on, because I have got a limit for explaining. This much explained. Tell me, Y becomes 0 for X equal to, fast. For X equal to, condition number 1, X equal to 0. And then, at the point B, YB equal to 0. Therefore, Y equal to 0 for X equal to, fast. X equal to, fast, tell me. I want to close now. X equal to, fast. X the point B, X is from here. X equal to, you are dealing L. Okay. This is the boundary condition for case 1. Case 2, tell the answer. Theta A is 0. Therefore, theta becomes 0 for X equal to 0. Deflection A point. YA equal to 0. Therefore, Y becomes 0 for X equal to 0. Then, at the point B, theta B equal to 0. Theta B equal to 0. Theta equal to 0 for X equal to L. YB equal to 0. Y becomes 0 for X equal to L. Clear or not? X equal to 0, theta 0, X equal to 0, Y 0, X equal to L, theta 0, X equal to L, Y 0. I can use anyone first. I usually use not theta, I usually use Y first. Okay, I'll do one thing now. Okay. When I solve, I usually use Y first, then theta. Okay, here, start this question. Third case. Point A, theta is there. YA equal to 0. Therefore, Y becomes 0 for X equal to 0. Then, that's all. At the point B, theta B equal to 0. Theta B equal to 0. Therefore, theta equal to 0 for X equal to L. Deflection at B 0. Therefore, Y becomes 0 for X equal to L. Here, at the point A, deflection at A is known. Deflection at the point A, Y equal to YA. It is a boundary condition. So y becomes ya for x equal to what? See, ya is a constant. Y equal to ya for x equal to first. Over. Here, y becomes ya for x equal to 0. Then at the point B, theta equal to 0. So theta equal to 0 for theta b equal to 0. Yeah, for x equal to L, and at the point B, deflection equal to 0. So y becomes 0 for x equal to L. Clear? Tell me, clear means okay. 0, fast. I will explain once again. First of all, not required to explain once again. What to do? See here. Start here, x equal to 0, y equal to 0, x equal to L, y equal to 0. Over. Next question. X equal to 0, theta equal to 0, x equal to 0, y equal to 0, x equal to L, theta equal to 0, x equal to L, y equal to 0. X equal to 0, y equal to 0, x equal to L, theta equal to 0, x equal to L, y equal to 0. X equal to 0, y is ya, you require it. It is Beku. X equal to L, theta 0 and y 0. And I forgot actually, want to make a note. I want to do. I already wrote, I won't change. But make a note. When I apply to next class for differential equation, at any point, I first consider y, then consider theta, because I always first will consider y, then theta. Why? Reason. Because theta comes only after y. Tell me, theta is equal to, see, first your equation is y. So I will use first y condition. Then if theta condition is there, I will use next one. So theta equal to dy by dx. So when I solve this question, I will write y equal to 0, then I will make theta equal to 0. Clear? Because theta comes after y, dy by dx. Tell me. Clear means okay. I explained lot of important things. You take a neat screenshot of this one and make one more note. When he goes for derivation, if theta and y both are 0, or if theta and y both are to be used, which one he will use first? Tell me. Which one? When I do next time, I will write y only first. Which one I will use first? If y and theta both are to be considered, which one I will use first? If y and theta both are to be considered, which one I will use first? Y or theta? Which one I will use first? No, not x equal to 0. Among y and theta, if both are to be considered, which of them I will use first? Y first or theta first? I will use y first or theta first? Y first. Y means Nannishta, Kannadadalli, Hindi, Mera mercy. Even you use other one also, nothing will happen. Same answer will come. But safer side, I will use y0. Y first. Okay, thank you. We will meet tomorrow. Not tomorrow, next class. Correctly take a screenshot, and if possible, anybody please send the screenshot to me in my number. Anybody can send to my official classroom number. That 80886, that number. (80) 886 number. Anybody can send. Not this by other number. The number where your group is there. Anybody can tell it, send it to me. A neat screenshot. So that next time I don't require. I can tell, I can see in my mobile, in the WhatsApp. Who will send it? A neat screenshot to my, not that number, to the official number for which groups are there. You know that 80886. That is your BSK group is in which batch? That batch. Send it to me. Okay, thank you.